This podcast was created as a supplemental learning resource for this course. The content is based on assigned course materials, including open educational resources, textbook chapters, instructor-developed explanations, examples, and applications connected to course topics. AI tools were used to help transform course material into a conversational podcast format, including the use of AI-generated narration. The AI narration is intended to make the material more engaging, accessible, and flexible for students. However, the podcast should not replace careful reading of assigned materials, reviewing course lectures, or completing course activities. Any interpretations, examples, or explanations included in the podcast are provided for educational purposes and are the responsibility of the instructor. Students should rely on the assigned readings, course lectures, and official course materials as the primary sources for exams, assignments, and class discussions.
When you first sit down in a behavioral sciences statistics class, there's this really heavy unspoken expectation.
Yeah, that everything you're about to learn is going to be just incredibly cold and calculated.
Exactly. Like perfectly objective. You walk in and it feels like you're, being handed these ancient, immutable laws of mathematics straight down from a mountaintop.
Right.
You just plug the raw data in, you turn the crank, you get the absolute truth, and, well, that's it. It feels very binary, very sterile.
Oh, completely. You're taught to view these statistical tests as flawless mechanisms that are just completely detached from human ego, which is honestly such a comforting illusion, isn't it?
It really is.
We desperately want to believe that science is this pristine machine. I mean, we like things to be clear-cut and entirely separated from human messiness, especially when we're dealing with something as inherently chaotic as human behavior.
Yeah, you want the math to be your perfect objective anchor.
Right, but the reality of how these tools actually came to exist is, well, it's so much more complicated and honestly a lot more entertaining.
And that's exactly the mindset we need to take into our deep dive today. If you're listening to this, you're likely an undergraduate stepping into the deeper waters of behavioral sciences, and you're looking at Chapter 7 from the Crump Lab statistics text.
The infamous ANOVA.
The analysis of variance.
Yeah.
And I want to set the tone right now for you. We are not going to spend this time just reading formulas out loud.
Please no.
Right. We're going to completely deconstruct the logic of this test. And we're starting with the fact that the pristine machine of statistics was actually built on a foundation of incredible academic pettiness.
It really is the ultimate academic soap opera. I mean, the tool we're looking at today, the ANOVA, it was developed by Sir Ronald Fisher.
Who is, universally recognized as one of the absolute titans of modern statistics.
Right. His work is essentially the bedrock of experimental design. But the context of his discovery wasn't just a bunch of scholars nodding in quiet agreement in some hallowed hall.
Far from it. Fisher invents this revolutionary statistical method, right? He has mathematically cracked the code on how to compare multiple experimental groups simultaneously, which, if you're a researcher, is the holy grail.
Oh, it changes everything.
So naturally, he tries to publish his findings in the most prestigious statistical journal of the era, which was Biometrica. But the editor of Biometrica is Carl Pearson.
Yes, the Carl Pearson. The Pearson correlation coefficient guy that you probably learned about earlier in the semester?
That exact guy. And Pearson flat out refuses to publish Fisher's work.
Wow.
And not because the math was flawed, but because they absolutely despised each other. They were locked in this bitter personal feud over previous academic disagreements.
I mean, think about the implications of that for a second. The foundation of modern scientific analysis, a tool we currently use to evaluate everything from the efficacy of life-saving medical treatments to clinical psychology interventions, was essentially stalled because two brilliant men couldn't stand the sight of each other.
It's unbelievable.
Fisher's genius was subjected to the ultimate gatekeeping by just pure interpersonal beef.
So Fisher has this world-changing mathematical framework, and the top journal shuts him out entirely. You know where he ends up having to publish the ANOVA?
Where?
In the Journal of Agricultural Science.
Oh, right. An agricultural journal.
Yeah. He had to essentially smuggle modern statistics into existence through papers about crop yields and, fertilizer treatments.
That is amazing.
And the source text points out that this feud didn't even die with him. It bled into the next generation. Years later, Carl Pearson's son, Egon Pearson, teams up with Jerzy Neyman to revise Fisher's ideas into the null hypothesis testing framework that we actually use today.
And let me guess, Fisher hated them for it.
True to form, he absolutely hated them for it.
It's a hilarious and honestly vital piece of history because it strips away that illusion of the mountaintop. Behind the intimidating Greek letters, behind the complex sums and distributions are just passionate, flawed, highly emotional human beings who are desperately trying to figure out how to separate truth from chance.
Yeah. The math didn't arrive perfect and sterile. It was hammered out through arguments and spite and intellectual warfare.
I think knowing that actually makes the math less intimidating. You know, if Fisher and Pearson could fight over it, we can certainly wrap our heads around it. So let's get into the actual utility of this tool.
Let's do it.
If I'm a researcher trying to map human behavior, I'm rarely satisfied just comparing two isolated things. The world is just too complex for that. Let's say I'm running a study on memory performance.
Okay.
I don't just have an encoding condition and a no encoding condition. I might have participants try to memorize words while listening to classical music, while listening to heavy metal, while sitting in absolute silence, and, I don't know, while dealing with a distracting flashing light. That's four distinct conditions.
Right. Or consider clinical psychology. You're testing anxiety interventions. You don't just want to know if cognitive behavioral therapy is better than doing nothing.
Because that doesn't tell you enough.
No.
Exactly. You want to compare CBT against mindfulness training, against a pharmaceutical intervention, and against a placebo control. You need a statistical framework that can digest that entire landscape of data simultaneously.
Which naturally leads to the big question that, honestly, every single student has when they reach this chapter. And it's a totally valid pushback.
Oh, I know exactly what you're going to say.
Right. Because I already have a tool for comparing means. It's my trusty t-test. I know how to use it. If I have 3 different study strategies, let's call them Group A, Group B, and Group C, why can't I just take my t-test and run 3 separate comparisons?
The old brute force method.
Yeah. I'll run Group A versus Group B, then I'll run Group B versus Group C, and finally I'll close the loop with Group A versus Group C. Why do I need to learn this entirely new, complex system called ANOVA when I already know how to compare averages?
It is the most intuitive question to ask. If you have a hammer that works, you want to view every single problem as a nail. But if you take that approach with multiple groups, you're going to run headfirst into a massive mathematical trap.
The inflated type I error.
Yes, inflated type I error.
We touched on this in previous chapters, but let's really unpack the mechanics of how that error inflates for the listener.
Let's think about what a type I error actually represents in the real world. Every time you run a statistical test, you are accepting a gamble. You are drawing a line in the sand, usually an alpha level of 0.05, and saying, I accept that there is a 5% chance that the difference I am observing right now is completely meaningless.
A false positive.
Exactly. You are accepting a 5% chance that the natural, random variation of human beings just happened to align in a way that looks like a real effect purely by accident. You might loudly declare therapy A is a breakthrough treatment, when in reality, it was just a fluke of the specific sample you happened to draw.
Because, if you take 2 groups of people and give them both the exact same sugar pill placebo, their average scores on an anxiety test are never going to be identical down to the decimal point.
Never.
There's always going to be some random distance between them just because people are different.
Exactly. Random sampling error is just a constant feature of the universe. So we accept our 5% risk on a single test. But here is a critical pause and think moment for you listening.
Okay, lay it on us.
What happens to your risk, that chance of grabbing a false positive, if you refuse to use ANOVA, and instead you just keep rolling the statistical dice, running t-test after t-test on the exact same data set?
Well, if I think about this probabilistically, it's kind of like rolling a 20-sided die, right?
That's a great analogy.
Because a 5% chance is 1 in 20. If I run 1 t-test, I'm rolling that die once. The odds of rolling a critical failure A1, representing my false positive, are, manageable. But if I have 3 groups and I run 3 separate t-tests, I'm rolling that die 3 times.
And the math changes.
Yeah, the probability of getting at least 1 false positive across those 3 rolls is no longer 5%. It's compounding.
And compounds dramatically. And 3 groups is a very modest experiment. Imagine an experiment with 5 different treatment groups. To compare every single group to every other group, you don't just run 5 tests.
Oh no, you have to run all the pairwise combinations.
Right. Group 1 versus 2, 1 versus 3, 1 versus 4, 1 versus 5, 2 versus 3, and so on. For 5 groups, that is 10 separate t-tests.
10 rolls of the 20-sided die.
And by the time you run 10 tests, your overall chance of making at least one type I error isn't 5% anymore. The math pushes it closer to a 40% chance.
Wait, 40%?
Yes. You are virtually guaranteeing that you will find a statistically significant result purely out of random noise.
That is genuinely terrifying from a research integrity standpoint.
Yeah.
You could build an entire academic career publishing papers about treatments that don't actually work simply because you went on a false positive fishing expedition.
T-hacking at its finest.
You just keep torturing the data with t-tests until it confesses to something.
Which is exactly what Fisher realized. He saw that comparing multiple groups required a structural gatekeeper, something that could evaluate the entire landscape of the experiment in one unified mathematical breath without inflating the error rate.
And that is the function of the ANOVA.
That's it. It acts as an overall test. Before you are ever allowed to pull out your t-test hammer and look at specific pairs, the ANOVA evaluates whether the group means, as a whole collective, differ from one another more than we would expect by random chance.
So it holds the line at your 5% alpha, you run one ANOVA, you take one 5% risk. It tells you either, yes, there is enough variation among these groups to warrant a closer look, or it tells you, no, the differences you're seeing are entirely consistent with random noise, stop running tests and pack it up.
That gatekeeping function is brilliant, but it introduces a linguistic paradox that trips up almost every single student who encounters it.
Oh, the paradox is infuriating. And it's the exact reason I struggled with this text initially. Here's the problem, right? My entire goal as a researcher is to compare the averages of my groups.
Right, the mean.
I want to know if the mean anxiety score for Group A is lower than the mean anxiety score for Group B. So why on earth did Fisher build a test that is called the analysis of variance?
It feels like a bait and switch.
It feels completely misaligned. It's like going to a bakery, walking up to the counter and ordering a medium rare steak. If I care about the means, why am I analyzing the variance?
It's the perfect analogy because it highlights the indirect brilliance of the method. To understand why we analyze variance to test means, we have to deeply conceptualize what variance actually is in the context of human behavior.
Okay, pop the hood for us.
Variance is simply the measure of how spread out our numbers are. How much do people differ from one another?
Okay, but how does the spread tell me about the center? How does variance tell me about the means?
Because the spread is composed of two entirely different forces. And understanding the tension between those two forces is the secret to unlocking the means. Let's imagine your experiment comparing 3 different study strategies.
Okay, I've got strategy A, B, and C.
You calculate the mean score for strategy A, strategy B, and strategy C. If you look at those 3 means, they're going to be spread out. They will vary from each other. We call this the variability between the groups. Now, ask yourself as a researcher, why are those means different?
Well, the optimistic answer is that they're different because my experiment worked. Because strategy A is genuinely a superior cognitive technique compared to strategy B. That's the signal I'm trying to detect.
That is the signal. That is the variance you forced onto the data through your experimental manipulation. But is that the only reason those 3 means might be different?
No, because even if the study strategies were totally useless and all equal, like we said earlier, random sampling error would still ensure the group averages weren't perfectly identical.
Right.
So the spread between the group means is actually a combination of 2 things. It's my brilliant experimental effect, plus a healthy dose of random noise.
Exactly. The between-group variance is effect plus error. Now, we need a baseline. We need to know how much of that spread is just noise. So how do we measure pure, unadulterated noise in an experiment?
Oh, we look inside the groups.
Yes. Look at the variability within a single group. Look exclusively at the 20 participants who all use study strategy A. They all received the exact same manipulation. They all sat in the same room, read the same instructions, used the same technique. But did they all get the exact same score on the final test?
Absolutely not.
Yeah.
You'll have a huge spread. Someone got 100%, someone got a 60%, because people have different baseline intelligences, different levels of motivation. Maybe someone didn't sleep well, maybe someone had a headache.
And because they all received the exact same experimental treatment, absolutely none of that variation can be attributed to your manipulation.
It's just life.
It is pure, unfiltered human chaos. It is individual differences. It is measurement error. It is 100% noise.
Okay, I see the architecture of Fisher's logic now. We have the variance between the groups, which is contaminated. It's our signal plus noise. And we have the variance within the groups, which is our pure noise baseline. So ANOVA is just weighing those 2 things against each other.
It is a literal ratio. The core mathematical engine of the ANOVA is the F ratio, named in honor of Fisher. It takes the variance between the groups and divides it by the variance within the groups. Or, to strip away all the statistical jargon and use the absolutely brilliant plain English formulation from the Crump Lab text, F equals what we can explain divided by what we can't explain.
Can explain over can't explain. That is such a powerful heuristic. Let's pause and think about that ratio as a physical scale. If we run our data through this conceptual formula and we get an F value of exactly 1, what is the universe telling us about our experiment?
If F equals 1, just look at the arithmetic. The numerator must equal the denominator. The variance we can explain is exactly equal to the variance we can't explain. The variation between our groups is the exact same size as the random chaos within our groups.
Which means my signal is completely indistinguishable from the background noise. It's like trying to have a whispered conversation at a heavy metal concert.
Exactly.
The effect of my study strategies, if there even is one, is completely drowned out by the natural variations in student performance. And f of 1 is essentially a statistical shrug.
It is the math telling you it has no idea if your manipulation did anything at all. Now, what if you run the calculation and your f value is 5?
Oh, if is 5, the math gets exciting. It means the numerator is 5 times larger than the denominator. The variation I can explain the differences caused by my specific study strategies is 5 times greater than the random noise of individual differences.
Right.
My signal is blasting through the noise. That immediately gives me the intuition that my experimental manipulation is a powerful, real-world force.
And conversely, you might calculate an f value of 0.5.
Which would be depressing. It means the denominator is twice as big as the numerator. The random, unexplainable noise is actually generating more variation than my experimental design. I'm explaining less than nothing, practically.
This conceptual ratio is exactly why ANOVA analyzes variance. You cannot confidently evaluate the means until you know whether the differences between those means are larger than the natural, messy variation of the humans generating them.
Okay, the why is firmly established. I understand why the bouncer is checking IDs, and I understand that he uses variance as his measuring stick.
Good.
Now we have to roll up our sleeves and look at the engine. We need to talk about the math. And I know the moment we start talking about sums of squares and degrees of freedom, a certain percentage of students instantly glaze over.
They absolutely do.
But if we follow the logic we just established, the math is incredibly intuitive.
It really is just an accounting system. We are taking the total amount of variation in an entire data set and sorting it into 2 distinct buckets.
Before we sort the buckets, let's make sure we are seamlessly integrating the terminology, because when you have a single independent variable, a factor, say, type of therapy, and you split that factor into 3 distinct levels or conditions.
Like CBT, mindfulness, and control.
Right. You are running what's called a one-way ANOVA. It's one way because you only have one independent variable, even though it has multiple categories.
Exactly. Now, if you had 2 independent variables, say you were testing, type of therapy, A&D, dosage level of a medication, simultaneously you'd be running a factorial ANOVA. And if you tested the same people multiple times, that's a repeated measures ANOVA.
Right.
But for our purposes today, focusing on the fundamental logic, we'll stick to the one-way design. One factor, multiple levels.
Let's ground this in the visual example from the text. I want you, the listener, to imagine a very simple spreadsheet. We have 3 experimental groups, Group A, Group B, and Group C. To keep the math from spiraling out of control, we only have 3 participants in each group. 9 people total.
9 total scores representing our dependent variable.
I'm going to read the actual scores from the text so we can mathematically reason through this. Group A's participants scored 20, 11, and 2. A huge spread.
Very noisy.
Group B scored 6, 2, and 7. Group C scored 2, 11, and 2.
Okay, so the first step in our accounting system is to figure out the total amount of chaos in the room. We need to calculate the total variation. And in statistics, we measure variation using sums of squares. So we are looking for SS total.
If I'm trying to capture the absolute total chaos in this entire data set, my instinct is that I need a baseline that represents 0 experimental knowledge. I need to pretend I don't even know what groups these people belong to.
Just throw them all in one big pool?
Exactly. I just have 9 random humans. If I add up all 9 of those scores and divide by 9, I get an overall average of exactly 7.
That is the grand mean. The grand mean is your ultimate baseline prediction. If you knew absolutely nothing about a participant's condition, if you were totally blind to the experiment and you had to guess their score, your mathematically safest guess is the grand mean of 7.
So to capture the total chaos, I just measure how far every single person deviated from that grand mean. The first person in Group A scored a 20. That is a massive 13-point deviation from the baseline of 7.
But here is where we have to explain why we don't just add up those raw deviations. If someone scored 13 points above the mean, and someone else scored 13 points below the mean, and you add those together,
they cancel each other out. A plus 13 and a minus 13 sum to 0. The math would tell me there is no variation at all, which is obviously a lie.
Right.
So I could just take the absolute values,
Right.
just drop the negative signs.
You could. And there are statistical methods that use absolute deviations. But Fisher, and statisticians in general, prefer to square the deviations. Why? Because squaring does two things simultaneously. First, it eliminates the negative signs, completely solving the cancellation problem. A -3 squared becomes a +9.
Okay, that makes sense.
But conceptually, squaring disproportionately punishes large deviations.
Oh, that's fascinating. Because a deviation of 2 squared is only 4. But a deviation of 10 squared balloons to 100. It exponentially weights the outliers.
Exactly. It treats large deviations as exponentially more important sources of chaos. So you take every single score, find its distance from the grand mean of 7, square that distance, and sum all 9 of those squared numbers together.
And that gives you the sum of squares total. For this specific data, the text tells us the SS total is exactly 302.
Okay, SS total is 302. That is our grand pi of variation. Now, the ANOVA magic happens. We slice that pi into our two buckets, the part my experiment can explain and the part it can't. Let's tackle the can't explain bucket first. The sum of squares for the effect, SS effect.
To isolate the variation caused purely by your experimental manipulation, we are going to perform a deliberate mathematical fiction. We are going to pretend that individual differences simply do not exist.
This is my favorite conceptual leap in the whole chapter. To do this, we calculate the average for each specific group. The mean of Group A's scores, which were 20, 11, and 2, comes out to 11. The mean for Group B is 5. The mean for Group C is 5. Now, we perform the fiction. We mathematically erase the individuals. We replace every single person's actual score with their group's mean.
We pretend that every single participant in Group A scored exactly an 11. Everyone in Group B scored exactly a 5. Everyone in Group C scored a 5.
The text gives this great anthropomorphic personality to the group mean. It says, pretend you are the mean for Group A. Your identity is 11. Someone walks up to you and asks, hey, what was the score for the first participant in your group?
And because you are the mean, you lack the capacity to perceive individual differences. You just confidently reply, I know that, it's 11.
Right. And they ask, what about the second person? You say, it's 11, they're all 11, am I missing something?
It's a perfect metaphor. By viewing the data strictly from the perspective of the group means, we eliminate all the within-group noise. All that is left is the between-group variation. So how do we quantify that?
We measure how far these new fictionalized scores deviate from the grand mean. We take Group A's mean of 11, subtract the grand mean of 7, which gives us a deviation of 4. We square that to get 16.
Right, and we do that for every data point's newly assigned group mean, and we sum them up. The math works out to an SS effect of exactly 72.
Stop and look at what we've achieved. The total chaos in the room was 302. Of that total, a chump equal to 72 can be perfectly explained simply by knowing which group a participant was placed in. Your experiment forced 72 units of variation onto this data.
Which naturally leads us to the second bucket. If the total is 302 and the effect is 72, simple algebra tells me that the leftovers of variation I can't explain must be 230. 302 minus 72 is 230.
Algebraically, yes. That is the sum of squares for error, SS error. But to truly understand the mechanism, we shouldn't just rely on subtraction. We need to calculate it directly to prove that it really represents the noise.
So if SS effect was calculated by pretending everyone scored exactly their group mean, SS error must be the reality check. It's measuring how far each actual human deviated from that group mean. It's quantifying the messy individual differences.
Exactly. Take the first person in Group A. They scored a 20, but their group mean was 11. That person deviated from the expectation of their group by 9 points. That is pure, unexplainable individual variance.
So we square that 9 to get 81.
We do this for all 9 participants, measuring their distance from their own specific group mean, squaring it, and adding it all up.
And when you sum up those 9 squared reality checks, the math miraculously lands on exactly 230. It's perfectly elegant. SS total, which is 302, perfectly equals SS effect 72 plus SS error 230. We have successfully sorted the variance into the two buckets. We have what we can explain and what we can't explain.
So if ANOVA is a ratio of those two things, can we just divide 72 by 230 and get our F value?
My instinct says no, because the scales are fundamentally mismatched. SS error, the 230, is the sum of 9 separate individual deviations. SS effect, the 72, is essentially derived from just the three group means.
Oh.
Obviously, a sum of 9 things is generally going to be larger than a sum based on 3 things, purely by volume.
Right. It's not a fair fight.
We can't compare the raw sums. We have to find the average variance for each bucket.
Precisely. We need to level the playing field. And to find the average variance, which we call the mean square, we have to divide each sum of squares by a very specific concept. It's degrees of freedom.
Okay, degrees of freedom, DF. This is the phrase that strikes absolute terror into the hearts of undergrads.
Oh, universally.
The way it's usually taught feels like statistical hazing. You're just handed a sheet of arbitrary formulas.
Right.
N minus 1, K minus 1, N minus K. Memorize them or fail. But if we look at degrees of freedom as a structural penalty for estimating, it becomes a logical puzzle instead of a memory test.
Let's reframe it entirely. Every time you calculate a mean in statistics, you are extracting information from your data, but you are also locking that data down. You are imposing a mathematical constraint. Imagine you have 3 numbers, and I tell you their mean is exactly 10.
Okay, 3 numbers, average is 10. That means they must sum to 30.
Exactly. Now, I ask you to invent the 3 numbers. The first number can be absolutely anything. You pick 100. The second number can be anything. You pick -50. Those 2 numbers were completely free to vary. But what about the third number?
It has no freedom at all. If the first 2 are 100 and -50, they sum to 50. But the total sum must be 30 for the mean to be 10. So the third number is mathematically forced with a gun to its head to be -20.
It lost its freedom the moment I imposed the constraint of the mean.
That is the essence of degrees of freedom. Now let's apply that to our ANOVA buckets. Let's look at the effect bucket. We have 3 group means, group A, B, and C. But we previously established they are constrained by the overall grand mean.
Right. 2 of those group means are free to be whatever they want, but the third one is forced to be a specific value so that they all average out correctly to the grand mean. So, out of 3 groups, only 2 are free.
The formula for the effect's degrees of freedom is simply the number of groups minus 1. In our case, 3 minus 1 equals 2 degrees of freedom.
Now apply that logic to the error bucket. To calculate the error, we had to measure deviations within all 3 groups, which means we had to calculate 3 separate group means. We imposed 3 constraints on the dataset.
Oh, this is clicking perfectly. In Group A, 2 people are free, but the third person is locked by Group A's mean. In Group B, 2 are free, the third is locked. Same for Group C. Out of 9 total people, 3 are mathematically locked down.
So the formula for the error's degrees of freedom is the total number of scores minus the number of groups. 9 minus 3 equals 6 degrees of freedom.
You've just derived the formulas intuitively. Now we can finally average our buckets. We take the sum of squares and divide by the degrees of freedom to get the mean square, or MS squares.
So mean square effect is 72 divided by 2, which gives us an average explainable variance of 36. And mean square error is 230 divided by 6, which gives us an average unexplainable variance of 38.33. We have completely leveled the playing field.
Which brings us to the moment of truth. Fisher's final ratio, F equals mean square effect divided by mean square error.
36 divided by 38.33.
We hit equals on the calculator and we get an F value of 0.939. We did it. We ran the manual ANOVA.
And based on the conceptual intuition we built earlier, what does an F value of 0.939 tell you about this data?
Well, it tells me I shouldn't be writing a Nobel acceptance speech anytime soon. It's less than 1. The denominator is slightly larger than the numerator. My average unexplainable noise is actually slightly louder than my experimental signal.
Yeah.
If this were a real experiment testing study strategies, I would have to concede that the strategies didn't seem to produce differences any larger than the natural chaos of the students.
Exactly. Now, in the real world of behavioral science, software like R, Python, or SPSS will do all of that arithmetic for you in a millisecond. It will generate a beautiful ANOVA summary table that perfectly organizes the sums of squares, the degrees of freedom, the mean squares, and the final F value into neat rows for effect and error.
But the computer output always includes one more column, a column we haven't calculated yet, and arguably the most misunderstood number in all of science.
The p-value.
The p-value. We have our F statistic of 0.939, but we need to know the probability of getting that F statistic. Where does that probability come from?
To deeply understand the p-value, we have to step outside of our specific data set and enter the realm of simulation. We need to construct a counterfactual universe.
And the Crump Lab text does this with what I think is a brilliantly unhinged thought experiment, the magic pills simulation.
It is the best way to visualize a distribution I have ever seen.
Okay, listen closely to this setup. Imagine we are running a massive high-stakes experiment. We are testing a brand new magic pill that is scientifically engineered to make you permanently smarter. We have one factor, dosage. And we have 3 levels. Group 1 takes 1 pill, Group 2 takes 2 pills, Group 3 takes 3 pills. Our dependent variable is a standardized smartness test.
We know the baseline parameters of this test. In the general population, it has a normal distribution with a mean score of 100 and a standard deviation of 10. We recruit 30 participants, 10 for each dosage group.
We run the experiment, we record the scores, we calculate the sums of squares, and we get an F value. There's one experiment. But here is the massive, crucial twist of the simulation. We, as the omniscient creators of this universe, know a secret.
The pills are just sugar.
They do absolutely nothing. They're physically incapable of altering human intelligence.
This is the critical conceptual leap. By ensuring the pills are sugar, we are intentionally enforcing the null hypothesis. We are creating a reality where we know with absolute 100% metaphysical certainty that there are no true differences between these 3 groups.
Right.
Any variation we see in the means is purely the result of random sampling error.
Because the pills do nothing, every single participant in the study is essentially just drawing a random smartness score from that exact same normal distribution centered at 100. Now, we program a computer to run this exact fake experiment, but we don't just run it once.
No, we run it over and over.
We have the computer run 30 random people, calculate the F value, and save it, then do it again and again. We run 10,000 completely separate iterations of this meaningless experiment.
10,000 distinct experiments generating 10,000 F values, all drawn from a universe where we know the true effect is 0.
We take all 10,000 of those F values and we plot them on a giant histogram. We want to see the shape of chance. This creates the F distribution. If you look at the graph of this in the text, there are 2 massive observations we have to make.
Okay, what's the first one?
First, the shape is completely asymmetrical. The smallest possible value on the x-axis is exactly 0. The graph just stops. Why are there absolutely no negative F values in 10,000 tries?
Think back to the math we just did. F is a ratio of mean squares. And how did we get the squares? We squared the deviations.
Right, a real number, when squared, cannot be negative.
Exactly. Therefore, both our variance can explain and our variance can't explain must be positive numbers. A positive divided by a positive is always positive. The F distribution is strictly bound at 0.
Okay, second observation. If you look at the bulk of the graph, the vast majority of these 10,000 fake experiments produced F values piled up right around 1 or even less than 1. It's a massive tower on the left side of the graph. Why?
Because of the design of the simulation. We engineered a universe where there is no real effect. So on average, the variance between the groups is just capturing the exact same random noise that the variance within the groups is capturing.
The numerator and denominator are roughly equal.
Yes. The can explain equals the can't explain. So the ratio naturally hovers around 1.
And this is where the danger of statistics lives. If you look closely at the right side of the graph, there's a long, thin tail stretching outwards. Some of these fake experiments produced an F value of 2. A few produced a 3. In extremely rare cases, the computer spit out an F value of 5 or 6.
Now, imagine you didn't know this was a simulation. Imagine you ran a real experiment, spent a year collecting data, and your software spit out an F value of 5. You would be ecstatic. You'd think, my signal is 5 times louder than the noise. I've discovered a massive effect.
But we know for a fact the pills were sugar. So how on earth did the math generate an F of 5?
Pure, unadulterated dumb luck. Just by chance, in maybe 10 out of those 10,000 experiments, the random number generator happened to assign all the naturally brilliant people who are going to score 120 anyway into the 3-pill group, and all the tired, distracted people who are going to score an 80 into the 1-pill group.
Oh.
The group means looked drastically different, creating a massive between-group variance, which resulted in a massive F value. Chance manufactured a mirage.
Which brings us back to type I errors and setting boundaries. As researchers, we need a line in the sand. We need to look at that distribution of chance and say, at what point is an F value so uniquely large that it's highly unlikely to be just a mirage?
We set our alpha criterion, our acceptable risk, at 5% or 0.05. We look at our histogram of 10,000 fake F values and ask the computer, what specific F value separates the bottom 95% of the data from the top 5% extreme tail? For this specific experimental design, the math tells us that critical value is 3.35.
So we draw a hard vertical line at 3.35. Exactly 5% of our 10,000 purely random sugar pill experiments produced an F value larger than 3.35.
This is how we make decisions in the real world. If you run a real experiment and you calculate an F value of 4.0, You compare it to that null distribution. You say, if my manipulation actually did nothing, chance alone would only produce an F value of 4.0 less than 5% of the time. That is rare enough that I'm willing to reject the idea that my manipulation did nothing. You reject the null hypothesis.
But even with that strict rule, if we apply it to our simulation, we are still going to be fooled 5% of the time. 500 out of our 10,000 sugar pill experiments crossed that line and looked significant.
Yes, that is the cost of doing business in inferential statistics. You will occasionally publish a false positive.
And this leads us to what is arguably the most pervasive, deeply entrenched misconception in all of science: the misinterpretation of the p-value. I hear graduate students, and honestly even some professors, say this: I got a p-value of 0.05. That means there's a 5% chance that the null hypothesis is true. There is a 5% chance my effect is fake.
Saying that in front of a statistician is a great way to watch them internally combust.
Right. The text is incredibly explicit about this. The p-value is categorically not the probability that the null hypothesis is true.
To understand why that interpretation is logically impossible, look back at our simulation. In our sugar pill universe, what was the probability that the null hypothesis was true?
It was 100%. We coded it that way. The null was an absolute fact of reality.
Exactly. The null hypothesis is a state of the universe. It either is entirely true or it is entirely false. It does not have a probability. The p-value cannot measure the probability of reality.
So what exactly is the p-value quantifying?
The p-value measures the probability of your data. Specifically, it is the probability of observing an F value as large as yours, or even larger, if we assume the null hypothesis is completely true.
Let me repeat that to lock it in. It is the likelihood of observing the data, given the assumption of the null. It is not the likelihood of the null, given the data. It is measuring how surprising your specific sample is, assuming chance is the only architect in the room.
It's a subtle philosophical distinction, but a mathematically vital one. And failing to grasp it leaves you vulnerable to what the CrumpLab text beautifully calls the siren song of chance.
Oh, this section is terrifying. The text takes 10 of those simulated sugar pill experiments, the ones that, by pure luck, produced a massive F value and a significant P value, and it plots their group means on standard bar graphs.
If you look at those graphs in isolation, they are incredibly seductive.
Seductive is the right word. If I'm a student and I look at simulation hashtag 32, the bar for the 3-pill group is towering over the 1-pill group. The standard error bars are tiny. There is absolutely no overlap. The visual evidence is overwhelming.
It looks perfect.
If I saw that graph in a published journal article, I would bet my life savings that those pills work. The effect looks undeniable.
But we, as the omniscient observers, know it is entirely a phantom. Those distinct, separate bars were drawn from the exact same uniform pool of data. Chance just happened to sort the numbers in a highly patterned way for that one iteration.
It proves that you cannot trust your eyes. Human beings are pattern-matching machines. We will see a real effect in random noise if the noise happens to look pretty. We have to respect the bounds of probability and remember that a beautiful graph can still just be a 1 in 20 statistical fluke.
Which brings us to another critical realization. Before we apply this to a real study, we need to talk about the boundaries of the mathematical models we are building. The ANOVA math is powerful, but it relies on certain structural assumptions about the reality of your data.
Right, the assumptions: normality, homogeneity of variance, and independence. Often taught as a checklist to panic over, but philosophically, they're just the terms of service for using Fisher's math.
Let's translate them. Normality just assumes that within each of your groups, the individual scores are distributed roughly like a bell curve. Homogeneity of variance, which is a mouthful, simply means that the spread, the noise, is relatively similar across all your different groups. Group A shouldn't have a massive variance of 100, while Group B has a tiny variance of 2.
And independence just means one participant's score doesn't influence another's. They aren't cheating off each other. But here's the critical question. What happens if my data is messy? What if my real-world human data violates the assumption of normality a little bit? Does the whole ANOVA shatter?
Not at all. One of the greatest features of the F statistic is that it is remarkably robust. Unless your data is wildly skewed or the variances between your groups are drastically orders of magnitude different, the ANOVA will still give you a very accurate approximation of reality.
So it's forgiving.
Very forgiving. It's a resilient tool. You don't need to panic at slight deviations from the ideal mathematical forms.
Okay, we've survived the theory, the math, the simulations, and the assumptions. We were ready to move into the real application. But there is one final limitation we have to establish: the bouncer analogy.
Ah, yes, the omnibus test.
All right, Let's say I run a real experiment. Real interventions, no sugar pills. I run the ANOVA, and I get an incredible F value of 6.0 with a P value of 0.001. A tiny probability that chance produced this. I have definitively beaten the null hypothesis. My experimental manipulation worked.
Yeah.
But do I know exactly which of my three groups was the best?
You do not. And this is the most common pitfall for students interpreting an ANOVA. The word omnibus comes from Latin, meaning for all or comprising several items.
I think the text says it sounds like a bus you want to ride, which is charmingly nerdy.
It is. But structurally, the omnibus ANOVA only tests one giant, overarching, generalized hypothesis. It tests the idea that the mean of group A equals the mean of group B equals the mean of group C. A equals B equals C.
Let's pause and think through the mechanics of that.
Yeah.
If all three groups are completely different from each other in reality, the between groups variance is going to be massive because the means are spread far apart. That gives me a big numerator, a big F value, and a significant result. But what if group A and group B are exactly identical, but group C is wildly, drastically different? Wouldn't that also make the between groups variance massive?
Yes, because group C pulls the overall variance wide open. And that scenario would also produce a large F value and a significant P value.
So a significant ANOVA simply rejects the blanket statement that A equals B equals C. It throws a red flag and says, hey, something is happening in here. At least one of these means is significantly different from at least one of the others.
Right.
But it is completely blind to where that difference is hiding. Is A different from B? Is A different from C? The omnibus test mathematically cannot tell you.
Which is why the bouncer analogy is perfect. The
Yeah.
ANOVA is the bouncer at the door of the nightclub. He checks your statistical ID. He ensures your overall variance is large enough to justify entry.
Right.
If it is, he unclips the velvet rope and says, yes, there is enough evidence of a real difference here. You are allowed inside to investigate. But he doesn't hand you a map to the VIP section. He doesn't tell you which specific groups are driving the difference.
So, to be incredibly explicit for anyone writing a lab report, you cannot look at a significant F statistic of 6.0 and confidently declare Group C outperformed Group A. The ANOVA did not give you the evidence to make that specific paired claim.
And conversely, we have to address the mirror image misconception. What if the bouncer denies you entry? What if you get a non-significant ANOVA, an F of 0.8 with a p-value of 0.50?
The temptation is to immediately write in the discussion section, this study proves there is no difference between these therapies in reality.
Which is logically flawed. A non-significant p-value does not mean no difference exists. It simply means that based on this specific, limited sample with this specific level of experimental noise, you failed to gather enough statistical evidence to confidently reject the null.
Absence of evidence is not evidence of absence. The therapy might actually work beautifully in the real world, but maybe my sample size of 10 people was too small to detect it. Or maybe my measurement tool was so flawed that it generated a massive amount of within-group noise that drowned out the signal. The effect might be there, we just couldn't hear it over the static.
The ANOVA is a measure of evidence, not a declaration of absolute reality.
Okay, we have laid all the groundwork. We are ready for the grand finale. Let's take everything we just learned, the variance, the buckets, the omnibus bouncer, the p-values, and apply it to a deeply fascinating piece of real-world behavioral science.
The Tetris and Trauma study by James and colleagues from 2015, it is a masterclass in why complex experimental design requires the ANOVA framework.
When I first read the premise of this study, I immediately pushed back. The research question sounds like pure clickbait pop psychology. Can playing the video game Tetris shortly after watching a traumatic, scary movie prevent you from developing intrusive, PTSD-like memories of that movie over the following week? It sounds absurd. Tetris cures trauma.
It sounds absurd until you understand the deep cognitive mechanisms they were targeting. The study is grounded in the theory of memory consolidation. When you experience a trauma, the memory isn't instantly locked into a permanent vault. It is malleable for a short window. The theory posits that trauma memories are highly visual and spatial. Tetris is a game that aggressively monopolizes the brain's visual spatial processing center. The researchers hypothesize that if you force the brain to dedicate all its visual spatial resources to rotating blocks, it physically will not have the bandwidth left to consolidate the visual traumatic memory. You are essentially starving the trauma of cognitive resources.
Okay, that is a profoundly elegant theory, but translating that into a rigorous experiment is hard. If they just had one group watch a scary movie and do nothing, and a second group watched the movie and played Tetris, that's just a two-group t-test. But human memory is more complex than that. What if the memory is already consolidated? Can you disrupt it later?
Which is why they utilized a brilliant 4-level experimental design. Let's map out the variables. The independent variable, our factor, is the treatment condition, and it has 4 distinct levels.
4 levels. Okay, level 1 is the baseline, the no-task control. They watched the horrific movie, and then instead of treatment, they just did a boring 10-minute music filler task.
Oh.
Level 2 is the full experimental intervention, reactivation plus Tetris.
Right.
First, they watch the movie. Then a day later, they are shown brief, specific images from the movie to actively reactivate the trauma in their working memory. While the memory is vulnerable and active, they immediately play Tetris for 12 minutes.
Now look at the control conditions they built to isolate the mechanism. Level 3 is Tetris only. They watch the movie, and a day later they play Tetris, but they are not shown the images. Their memory is not actively reactivated prior to gameplay.
And level 4 is reactivation only. They watch the movie. A day later, they're shown the traumatic images to reactivate the memory, but they do not play Tetris afterward.
By breaking it into 4 levels, they can isolate exactly what is causing a change if a change occurs. The dependent variable, what they are measuring, is the mean number of intrusive, unwanted memories the participants record in a daily diary over the following week.
So we have 4 independent groups. Because we have 4 groups, we absolutely cannot just grab our t-test hammer and start comparing level 1 to 2, 1 to 3, 1 to 4, 2 to 3. We'd inflate our type I error into the stratosphere. We need the omnibus ANOVA to act as our gatekeeper.
So they collect the diaries, calculate the means, and run the data through the software. The text provides the visual bar graph first.
And visually, it looks promising. The bar representing the mean number of intrusive memories for the reactivation plus Tetris group is noticeably lower than the other 3 bars. But we know better than to trust the siren song of a pretty graph. We need the mathematical output.
The researchers report their ANOVA results in standard APA formatting. It reads F368 equals 3.79, P equals 0.014.
Let's translate that entire sentence for the listener, using the math we just learned. Let's start with the parentheses. F368, those are our degrees of freedom. The first number 3 is the DF for our effect. The formula is groups minus 1. They had 4 conditions. 4 minus 1 is 3. The math is perfect.
The second number, 68, is the DF for error. The formula is total scores minus groups. The text notes there were 72 total participants in the study. 72 total humans minus 4 group constraints equals 68. The accounting is flawless.
Next, the F value is 3.79. It is significantly larger than 1. This tells us that the variance we can explain through our 4 conditions is nearly 4 times larger than the variance we can't explain from individual human differences. The signal is beating the noise.
And finally, the p-value is 0.014. Our standard alpha threshold, our line in the sand, is 0.05. Because 0.014 is less than 0.05, we have crossed the threshold into statistical significance.
To phrase that in rigorous counterfactual terms, if the Tetris interventions did absolutely nothing and all 4 groups were just generating intrusive memories based on completely random individual differences, an F statistic of 3.79 or larger would only occur by chance 1.4% of the time. Because that probability is so low, we reject the idea that chance alone produced this data.
The bouncer has unclipped the velvet rope. The omnibus test has officially declared there is a mathematically significant difference somewhere among these 4 means. But remember, the ANOVA stops there.
Right. The omnibus ANOVA doesn't know which specific therapy combination worked. To find out, we have to run post hoc tests, follow-up tests. Because the ANOVA gatekeeper gave us clearance, we are now allowed to pull out the t-tests and compare specific pairs.
The researchers naturally start with their primary hypothesis. Did the full intervention work? They run a post hoc t-test comparing the no-task control group directly to the reactivation plus Tetris group.
The result: a t-statistic of 2.99 with a p-value of 0.005. Highly significant. The group that got their memory reactivated and then played Tetris experienced significantly fewer intrusive memories than the control group. The cognitive starvation theory seems to hold weight.
But here is where the multi-level design proves its worth. What about the people who just played Tetris without getting the memory reactivated first? Is Tetris alone a magic cure for trauma? They run a t-test comparing the control group to the Tetris-only group.
The text notes the p-value for that specific comparison is 0.318. Let's think about that. 0.318 is massively higher than 0.05. It is not significant.
It is not even close to significant. The difference between playing Tetris alone and doing nothing could happen by random chance nearly 32% of the time.
That is the crucial insight. Just firing up a Game Boy after a trauma, does not protect your brain. The memory must be actively brought back into a vulnerable, malleable state in your working memory, the reactivation phase before the visual spatial processing of Tetris can disrupt it.
This brings up a vital lesson about effect size and practical meaning. The ANOVA provided statistical significance. It proved the signal was real. The post hoc tests provided the location of the signal, but the experimental design provided the meaning.
You can have a statistically significant result that is practically meaningless in the real world if the effect size is tiny. But here, the pattern of the means tells a profound story about how human memory operates. We only uncovered that specific nuanced mechanism because Fisher's mathematical framework allowed us to rigorously structure and analyze the variance across 4 distinct realities simultaneously.
It is a stunning marriage of cognitive psychology theory and robust statistical architecture. You truly cannot have one without the other. The math without the theory is just number crunching, and the theory without the math is just philosophy.
Wow. We have traversed an immense amount of intellectual terrain today. To ensure this all gels into a cohesive mental model for the listener, let's do a rapid, high-level structural review.
We started by dismantling the sterile illusion of statistics. We looked at Ronald Fisher, circumventing a petty academic feud with Carl Pearson, to publish the foundational ANOVA in an agricultural journal. The math is a product of human argument.
We recognize the trap of the t-test. If you try to compare multiple groups by rolling the statistical die over and over, you inevitably inflate your type I error. You guarantee false positives. You need the ANOVA to act as a unified gatekeeper.
We resolve the paradox of analyzing variance to understand means. By comparing the variance we can explain, the spread between our groups, to the variance we can't explain, the individual noise within our groups, we generate the F ratio.
We mathematically separated the signal from the noise using sums of squares, squaring the deviations to eliminate negative signs and punish the outliers. We imposed degrees of freedom as a necessary structural penalty for estimating means, which allowed us to calculate the mean squared error.
We conceptually built the F distribution by simulating 10,000 fake sugar pill experiments. This allowed us to deeply understand that a p-value is not the probability that the null is true, but rather the probability of our data occurring in a universe where the null is a fact. We learned to distrust the siren song of a lucky graph.
And finally, we acknowledged the limits of the omnibus test. A significant ANOVA just proves that A does not perfectly equal B, which does not perfectly equal C. It gives you permission to run post-hoc analyses like we saw in the elegant Tetris and trauma study to discover exactly where the true differences lie.
It is a profound, incredibly logical progression of thought once you strip away the intimidation of the formulas.
It really is. But before we sign off, I want to pivot away from the strict math. I want to leave you, the listener, with a slightly more philosophical, provocative thought. Something to chew on as you head into your stats lab and start crunching this data for yourself.
It is so easy, once you learn an ANOVA, to rigidly divide the world into 2 neat categorical boxes. We have the variation we can explain, which we proudly claim as our brilliant Nobel-worthy experimental effect. And we have the error variance, the within-group differences, which we somewhat arrogantly dismiss as just the random annoying noise we can't explain.
But if you want to be a true behavioral scientist, a true observer of human nature, you have to ask yourself a deeper question about that noise. How much of that random error variance is actually just the impact of other incredibly fascinating psychological variables that we simply weren't smart enough to measure in this particular study?
Think about it. That participant in Group A who scored a 20 while the rest of the group averaged an 11, maybe their score isn't just a statistical glitch. Maybe they aren't just error.
Maybe they had a unique genetic trait. Maybe they had a specific childhood trauma that interacted with the therapy in an unexpected way. Maybe they have a totally distinct cognitive coping mechanism that we haven't even named yet.
Exactly. We call it noise because it is mathematically convenient for this specific ANOVA. But in reality, what we label as noise is almost always just a complex signal that we haven't tuned our scientific instruments to hear yet. Today's unexplained error variance is tomorrow's groundbreaking, independently measured factor.
Today's noise might be tomorrow's signal. That completely flips the perspective, and it brings us all the way back to the very beginning of our conversation. Statistics isn't a flawless, objective X-ray machine. It is a messy, deeply human endeavor. It was born out of arguments between flawed men, and we use it to try and map the chaotic, endlessly nuanced reality of human behavior.
We use the math to try and impose a temporary scaffolding of order onto that chaos. But the chaos is where the real truth of humanity is actually hiding. The variance is the story.
Thank you so much for joining us on this extensive deep dive into Chapter 7. Take this conceptual intuition, hold on to the logic of the F ratio, and bring it directly into your stats lab. You don't just know the formulas now, you know why they exist. You've got this. We'll see you next time.